You already know this story. Isaac Newton. An apple falls from a tree, it hits him on the head, or lands nearby depending on which version you heard. In that moment of mundane collision, something clicks. He looks up at the moon. He looks down at the apple. He understands, suddenly, that the same force pulling the apple to the ground is holding the moon in its orbit. Gravity, the universal law. 1666. Almost none of this is true. Not the apple hitting his head. That detail was added later for dramatic effect. Not the sudden revelation. Newton worked on the problem of gravity and planetary motion for more than 20 years before publishing his theory. Not even the idea that he invented gravity, as if gravity required inventing. What Newton did was something more remarkable and more complicated than the legend suggests. And what Einstein did, 2.5 centuries later, was something that most people have heard of, but almost nobody fully understands. Because here is the thing about gravity that almost no one tells you. Newton described it, Einstein explained it, and what Einstein explained is this. Gravity is not a force. It is a shape. It is the curvature of space-time itself, caused by the presence of mass. And what we experience as the pull of gravity is not a force acting on us at all. It is us following the natural path through a curved universe.
This is not a metaphor.
It is not a simplification for a general audience. It is, as precisely as language can express it, what general relativity actually says. By the end of this, you will understand gravity in a way that most people never do, and you will understand why the difference between Newton and Einstein is not just a matter of physics. It is a matter of what it means to understand the world. To understand what Newton achieved, you have to understand the world of natural philosophy before him. In 1600, the dominant framework for understanding the motion of objects, the framework that had governed educated thought for nearly 2,000 years, was Aristotelian physics. The universe, according to Aristotle, was fundamentally divided into two realms, the terrestrial and the celestial. In the terrestrial realm, the Earth and its immediate surroundings, objects had natural places toward which they moved. Heavy things like earth and water moved downward toward the center of the universe. Light things like fire and air moved upward. The motion of falling objects was not caused by a force. It was caused by objects seeking their natural place.
In the celestial realm,
The moon, the planets, the stars, objects moved in perfect circles because circular motion was the only perfect, eternal kind. The rules that governed the heavens were entirely different from the rules that governed the earth. This division between terrestrial and celestial physics, between the rules of the ground and the rules of the sky, was considered self-evident. It was not a scientific hypothesis, it was a philosophical certainty. Galileo Galilei began to undermine it in the early 17th century. His telescopic observations showed that the moon had mountains and craters. It was not a perfect crystalline sphere, but a physical object, textured and irregular, more like the Earth than like a mathematical abstraction. His observations of Jupiter's moons showed that not everything in the heavens moved around the Earth. His experiments on motion, the inclined planes, the balls rolling across surfaces, the thought experiments about falling objects, established that the acceleration of falling bodies was constant, regardless of their weight. The heavier object did not fall faster, as Aristotle had said. They fell at the same rate. He did not explain why. He described the fact. Johannes Kepler, working from the extraordinary observational data of Tycho Brahe, had by 1619 established 3 laws of planetary motion, precise mathematical descriptions of how the planets move around the Sun. The planets moved in ellipses, not circles. The rate at which they swept out area was constant. The relationship between their orbital periods and their distances from the Sun followed a precise mathematical rule. Kepler did not know why these rules held. He had described the motion of the planets with unprecedented precision. He had no explanation. The explanation fell to Newton. Isaac Newton was born on Christmas Day, 1642, in Woolsthorpe, Lincolnshire. His father, also Isaac, had died 3 months before he was born. His mother remarried and left him to be raised by his grandmother. He was a solitary, difficult child who built mechanical models and conducted amateur experiments and showed few signs in early life of the extraordinary mind that would emerge. He entered Trinity College, Cambridge, in 1661. The university was teaching Aristotelian physics. Newton, characteristically, taught himself from the works of Descartes, Kepler, and Galileo, and found them more convincing. In 1665 and 1666, the university was closed because of the plague. Newton retreated to his family home at Woolsthorpe. It was in this period, the famous Annus Mirabilis, the miraculous year, that he later said his mind was at its most fertile. He developed the foundations of calculus, he began his work on optics, and he began thinking about gravity. The apple story dates from this period. Whether an apple fell or not is almost beside the point. What Newton did was ask a question that no one had asked quite so precisely before. If the Earth attracts objects on its surface, does it also attract the Moon? And if so, can the same mathematical law describe both? He made a calculation. If the force of gravity decreases with the square of the distance, if doubling the distance reduces the force to 1/4, then the Moon, which is roughly 60 times farther from the Earth's center than an object on its surface, should experience a gravitational force that is 60 squared, or 3,600 times weaker. He compared this to the actual observed motion of the Moon. The numbers matched, but not perfectly, not with the precision Newton required. He set the calculation aside. He continued working on other things: optics, alchemy, theology. He did not publish. For nearly 20 years, the calculations sat incomplete. The problem was partly the accuracy of the available measurements of the Earth's radius, which was not yet well established. In 1682, improved measurements became available. Newton redid the calculation. This time, the numbers matched beautifully. He reportedly was so overwhelmed by the result that he had to ask someone else to finish the arithmetic. His Philosophiae Naturalis Principia Mathematica, the mathematical principles of natural philosophy, was published in 1687, more than 20 years after the apple-strewn summer of 1666. It is, by widespread consensus, the most important scientific book ever written. The law of universal gravitation, as Newton stated it, is this: every mass in the universe attracts every other mass with a force that is proportional to the product of the two masses and inversely proportional to the square of the distance between them. This is a statement of extraordinary power and scope. It applies to an apple and the Earth. It applies to the Earth and the Moon. It applies to the Sun and the planets. It applies to stars in distant galaxies and to the galaxies themselves. It is universal. It holds everywhere, at every scale, for all matter. The inverse square law, the fact that the force decreases with the square of the distance, has a beautiful geometric justification. The surface area of a sphere grows as the square of its radius. Gravity, spreading outward from a source like light from a lamp, must thin out at the same rate as the surface it fills grows. The inverse square law is the shape of three-dimensional space, written in the language of force. Newton's theory allowed astronomers to predict the positions of planets with extraordinary accuracy. It allowed the prediction of the return of Halley's Comet. It allowed the calculation of the mass of the Earth and the Sun. It allowed the discovery of Neptune, a planet whose existence was inferred from the gravitational perturbations it caused in the orbit of Uranus, before anyone had seen it directly. For 200 years, Newton's theory of gravity was not just the best description of gravity, it was considered complete. It was the model of what a scientific theory should be: universal, mathematically precise, predictive, and confirmed by every observation.
There was, however,
One nagging problem. Newton's theory had no mechanism. It described how gravity behaved with extraordinary precision, but it provided no explanation of how one mass could attract another across empty space. Newton himself was explicit about this. He coined the phrase "action at a distance" and noted with some discomfort that he had no hypothesis about how the force was transmitted. "I feign no hypotheses," he wrote. He described. He declined to explain. The explanation would come from someone born 2 years after Newton died. Albert Einstein was born in Ulm, Germany, in 1879. He was not, contrary to legend, a poor student. He was an excellent student in mathematics and physics. What he was resistant to was authority, the kind of rote learning and institutional deference that the German educational system of his era required. He did not fit well into the structure. After graduating from the Zurich Polytechnic in 1900, he failed to secure an academic position. The professors who might have recommended him found him too independent, too argumentative, too inclined to question rather than accept. He worked briefly as a teacher before securing, in 1902, a position as a patent examiner in the Swiss Patent Office in Bern.
the patent office gave him a steady income.
And crucially, time to think. His job was to evaluate patent applications, to read technical descriptions of inventions and determine whether they were novel and workable. He became very good at it. He was also, in the hours between patent applications, working on physics. In 1905, his own Annus Mirabilis, a year that produced 4 papers, each one of which would have made the career of an ordinary scientist. Einstein published The Special Theory of Relativity, the photoelectric effect paper that would eventually win him the Nobel Prize, and the paper introducing E equals mc squared. Special relativity was concerned with the relationship between space and time, specifically with what happens when you measure the speed of light from different reference frames. The answer, counterintuitively, is that the speed of light is always the same, regardless of how fast the observer is moving. This constancy requires that space and time are not absolute and separate, as Newton had assumed. They are relative, and they are woven together into a single 4-dimensional fabric, space-time.
This was radical.
But it was not yet a theory of gravity. Special relativity described physics in the absence of gravity, in what physicists call an inertial reference frame, a frame that is not accelerating. Gravity causes acceleration, and what happens to space and time in the presence of acceleration? Einstein spent 10 years finding out. In 1907, while working at the patent office, Einstein had what he later described as the happiest thought of his life. He imagined a man falling freely, specifically, a man in a sealed box falling freely in a gravitational field. If the box has no windows, the man inside cannot tell whether he is stationary in empty space with no gravity or falling freely in a gravitational field. In both cases, he floats. In both cases, if he releases an object, it floats beside him. The effects of gravity are completely absent from his experience, even though he is in a gravitational field.
This is not a simple observation.
It is the foundation of general relativity. It suggests that there is a fundamental equivalence between being in a gravitational field and being in an accelerating reference frame. This is the equivalence principle. The local effects of gravity are indistinguishable from the effects of acceleration. The implications took Einstein years to work through. If gravity and acceleration are locally equivalent, then gravity must affect everything that acceleration affects, including light. A beam of light in an accelerating box curves toward the floor of the box. Therefore, in a gravitational field, light must also curve. This was a prediction that Newton's theory did not make. Newton's gravity acted on mass. Light, being massless, should not be affected by gravity in the Newtonian framework. Einstein's framework said otherwise. But the mathematics required to express all this was more advanced than anything Einstein had learned. He needed a framework for describing curved spaces, a branch of mathematics called differential geometry or Riemannian geometry, developed by the mathematician Bernhard Riemann in the 1850s, but with no previous connection to physics. Einstein spent years mastering this mathematics, often with the help of his friend Marcel Grossmann, a mathematician who had studied it and could guide him through the parts he didn't know. The mathematics was not just difficult, it was, by Einstein's own account, the hardest intellectual work of his life. He described the 10 years between the equivalence principle and the final field equations as a period of constant struggle, frequent error, and gradual illumination. On the 18th of November, 1915, Einstein presented to the Prussian Academy of Sciences in Berlin a set of equations that he had been working toward for a decade. They are called the Einstein field equations. The equations are compact. They can be written in a single line using the notation of tensor calculus. Their content is enormous. They say, in mathematical language, that the curvature of space-time at any point is determined by the distribution of mass and energy at that point. Mass and energy tell space-time how to curve. Curved space-time tells mass and energy how to move. This is the core of general relativity, and it is a fundamentally different picture of gravity from Newton's.
In Newton's picture,
gravity is a force between masses. Mass A pulls on mass B across empty space at a distance instantaneously. There is no medium, no mechanism, just a mathematical relationship that happens to describe what masses do. In Einstein's picture, there is no force at all. What there is geometry. Mass curves the space-time around it. Other masses moving through that curved space-time follow the curves, not because they are being pulled, but because the natural path through curved space-time is what we call the path of a falling object. Imagine a heavy ball placed on a stretched rubber sheet. It creates a depression, a curve in the sheet. If you then roll a smaller ball across the sheet, it will curve toward the depression, not because the heavy ball is pulling it, but because the sheet itself is curved. This is an analogy, and like all analogies, it has limitations. But it captures something real about the geometry of the situation. The curvature of the medium determines the paths of the objects moving through it. In the real universe, the medium is four-dimensional space-time. The curvature is produced by mass and energy, and the paths are what we call orbits and trajectories and falls.
general relativity
made a specific prediction that Newton's theory did not, that light would be deflected by gravity, not just deflected by a specific, calculable amount. If you measured the apparent positions of stars near the Sun during a total solar eclipse, when the Sun's glare was blocked and stars near its edge became visible, the stars should appear slightly displaced from their true positions because the Sun's gravity was bending the light coming from them. The prediction was made in 1915. Testing it required a solar eclipse in which stars near the Sun's edge were visible. The next suitable eclipse would occur on the 29th of May, 1919. The war was still being fought when the prediction was made. Britain and Germany were enemies. Einstein was German. But Arthur Eddington, a British astronomer and a Quaker with principled objections to war, was determined to test the theory. He organized 2 expeditions to observe the 1919 eclipse, one to Sobral in Brazil and one to Principe, an island off the west coast of Africa. On the day of the eclipse, the weather at Principe was threatening. Clouds covered the sky for most of the morning. Eddington later wrote that he barely had time to observe the eclipse at all. He was processing plates, not observing.
but the clouds cleared.
Just long enough. The photographs were taken. When Eddington analyzed the plates, the result was clear. The stars near the Sun's edge were displaced from their true positions. The displacement matched Einstein's prediction. On the 6th of November 1919, at a joint meeting of the Royal Society and the Royal Astronomical Society in London, the Astronomer Royal J.J. Thomson announced the result. The front pages of newspapers around the world carried the story the next day. Einstein became, overnight, the most famous scientist in the world. The Times of London ran the headline, "Revolution in Science, New Theory of the Universe, Newton's Ideas Overthrown." Newton's ideas had not been overthrown exactly. General relativity reduces to Newtonian gravity in the limit of weak fields and slow speeds. For the purposes of most everyday calculations, Newton is accurate enough. But the picture of the universe that general relativity described, the curved, dynamic space-time in which gravity is geometry rather than force, was genuinely revolutionary. Between 1915 and the present, the predictions of general relativity have been tested with extraordinary precision. Every test has confirmed the theory. Mercury's orbit had a precession, a slow rotation of the ellipse, that could not be explained by Newton's theory. Small perturbations from other planets accounted for most of it, but a residual discrepancy of 43 arc-seconds per century remained unexplained. Einstein's general relativity predicted this precession exactly. It was the first confirmation that his theory did something Newton's could not. Gravitational time dilation, the prediction that clocks in a stronger gravitational field run slower than clocks in a weaker one, has been confirmed by experiments using atomic clocks at different altitudes. A clock at sea level runs slightly slower than a clock on a mountaintop. The difference is tiny, but it is real, and it is measurable. Gravitational waves, ripples in the fabric of space-time produced by accelerating masses, were predicted by general relativity in 1916. They were not directly detected until 2015, when the LIGO detector measured the space-time distortion produced by 2 black holes merging more than 1 billion light-years away. The distortion they detected was about 1,000th of the diameter of a proton. The detection of this signal, the quietest sound ever heard, the smallest deformation ever measured, confirmed a prediction that Einstein had made 100 years earlier. It also opened a new era of astronomy, allowing observations of cosmic events that produce no light but produce gravitational waves. Black holes, objects whose gravity is so strong that not even light can escape, are a direct prediction of general relativity. Einstein himself doubted they were real. In 2019, the Event Horizon Telescope, a network of radio telescopes coordinated across the globe, produced the first direct image of a black hole at the center of the galaxy M87. It matched general relativity's predictions exactly. In 2022, the same collaboration produced an image of the black hole at the center of our own galaxy, Sagittarius A star. General relativity has been tested in the most extreme environments in the universe, at scales from laboratory experiments to billion-light-year cosmic events, and it has not been wrong. Here is the most immediately practical consequence of Einstein's theory. The GPS system in your phone uses a network of satellites in orbit around the Earth. Each satellite carries an atomic clock. Your phone determines its position by comparing the timing signals from multiple satellites and triangulating.
The accuracy of this system
Depends on the atomic clocks on the satellites being precisely synchronized with the clocks on the ground. And here is where relativity becomes engineering rather than philosophy. The satellites are moving relative to the ground. Special relativity predicts that their clocks should run slightly slow due to their velocity, about 7 microseconds per day slower. But the satellites are also farther from the Earth's center. General relativity predicts that their clocks should run slightly fast, because they are in a weaker gravitational field, about 45 microseconds per day faster. The net effect? The satellite clocks run about 38 microseconds fast per day relative to clocks on the ground. 38 microseconds sounds trivial, but GPS requires nanosecond-level precision. An uncorrected error of 38 microseconds per day would cause GPS positions to drift by roughly 10 kilometers per day. Your phone would not know what city you were in. The GPS system corrects for this. The clocks on the satellites are adjusted before launch to account for relativity. The software running the system applies relativistic corrections continuously.
Every time you use GPS,
To navigate, to find a restaurant, to track a delivery, you are using a system that would fail without corrections derived from both special and general relativity. The curvature of spacetime, which is the actual mechanism of gravity, is not a theoretical abstraction. It is an engineering parameter that has to be accounted for in the design of a navigation system that 4 billion people use every day. Einstein did not set out to improve navigation. He was trying to understand the universe. The universe turned out to have GPS in it. General relativity is almost certainly not the final word on gravity. The theory has two problems at its edges, two regimes where it breaks down, or at least where it gives results that cannot be right. The first is the singularity problem. At the center of a black hole, and at the moment of the Big Bang, general relativity predicts infinite density, a singularity. In physics, an infinity in a prediction is almost always a sign that the theory has reached its limits, that something is being left out. No one believes the density at the center of a black hole is actually infinite. General relativity says it is. That means general relativity is missing something.
the second problem
Is quantum mechanics. General relativity describes the large-scale structure of the universe, the behavior of planets, stars, galaxies, space-time itself. Quantum mechanics describes the small-scale behavior of particles, atoms, photons, electrons, the fundamental constituents of matter. Both theories are extraordinarily successful in their own domains. Both have been tested to extreme precision. and they are deeply, profoundly incompatible with each other. Quantum mechanics requires a flat, fixed background spacetime. General relativity says spacetime is dynamic and curved. The two theories cannot both be right as fundamental descriptions of reality. One of them, probably both of them, is a limiting case of a deeper theory that we do not yet have. The search for a quantum theory of gravity, for a framework that reconciles general relativity with quantum mechanics, has been the central, unsolved problem in theoretical physics for more than 50 years. String theory, loop quantum gravity, and various other approaches have been proposed. None of them has yet made testable predictions that confirm them over their rivals. None of them is established. We do not know how gravity works at the smallest scales. We know it curves spacetime. We do not know what spacetime is made of, or whether it is made of anything at all in the quantum sense.
Newton said,
I feign no hypotheses. I describe what I observe. 2.5 centuries later, Einstein explained what Newton had described. We are still waiting for whoever explains what Einstein described. Let me try to say, as clearly as language allows, what we currently understand gravity to be. Gravity is the curvature of spacetime caused by the presence of mass and energy. Spacetime, the four-dimensional fabric in which all events occur, is not a fixed, rigid background. It is flexible. It responds to matter and energy. Where matter is present, spacetime curves. The more mass, the greater the curvature. Objects moving through this curved spacetime follow what are called geodesics, the straightest possible paths through curved space. On the surface of the Earth, a geodesic on a flat map looks like a curve. On a globe, it is a great circle. In curved spacetime, a geodesic that looks curved to us, the arc of a thrown ball, the orbit of the moon, is actually the straightest possible path through the local geometry. What we feel as the pull of gravity is not a pull at all. It is the resistance of the ground to our natural tendency to follow the geodesic, the path through curved spacetime that without the ground in the way, we would follow all the way to the center of the Earth. Right now, sitting wherever you are not in free fall. The ground is pushing you upward, preventing you from following your natural gravitational path. You feel this upward push as your weight. What you experience as being held up is, in the language of general relativity, being prevented from falling. The person in an elevator in free fall, plummeting, weightless, is closer to the natural state than the person standing on the ground. This is the picture that Einstein gave us. It is strange. It is counterintuitive. It requires you to think about space and time not as the neutral stage on which physics occurs, but as a dynamic participant in the physics itself. And it is, as best we can tell, correct. Let us return to the apple. Not the legendary apple that hit Newton on the head, the actual apple, any falling object, any moment when something released from a height falls toward the ground. In Newton's picture, the apple is pulled by the gravitational force of the Earth. The Earth's mass attracts the apple's mass. The apple accelerates downward. The force acts at a distance, instantaneously, through some unspecified mechanism. In Einstein's picture, the Earth's mass curves the space-time around it. The apple, released from its branch, is no longer supported. It follows the geodesic, the natural path through the curved space-time, which curves toward the center of the Earth. There is no force, there is only geometry. Both pictures predict the same trajectory for the apple. For almost every practical purpose, Newton's picture is sufficient. It gives you the right answer to engineering accuracy. The GPS correction aside, you can build a bridge, launch a rocket, predict an eclipse, calculate a comet's return. All of it works with Newton. But the deeper truth, the actual description of what is happening when the apple falls, is Einstein's. The apple is not being pulled. The apple is falling along the straightest possible path through a universe that mass has bent. Newton asked, "What is the law that governs this falling?" Einstein asked, "Why does mass cause this falling at all?" His answer, that mass curves spacetime and falling is following that curvature, is the deepest understanding of gravity that human beings currently possess. It is also not the final understanding. Someone, someday, will ask the next question, and the universe, patient and precise and indifferent to our narratives about it, will have an answer ready. The apple falls. It always fell. We are still learning what that means.